All right, so today's physics video is about power. Let's get to it.
First of all, let's start with the definition of power. Power is the rate at which work is done. It is how quickly you do work. To simplify it a little bit, it's how much the energy changes or how much work is done per second or per unit time. Okay? So to calculate it, all you do is to find the power, you take the work and divide it by the amount of time it took to do that amount of work. All right? Probably the easiest way to do this would be to do an example. So here we go. Example number 1. Roy is going to lift a 20 kilogram box up 3 meters in 4 seconds, and we need to figure out how much power was used. Okay? So the first thing we're going to do is get a good appreciation of what's happening. So as usual, I like to make a drawing. So here we go. Little box. 20 kilograms is the mass of the box, and we are going to lift it up here to a height of 3 meters. It is still a 20 kilogram box. Okay, so because we're talking about energy changing, we want to be thinking about height and velocity. So we can think about GPE and KE. So we know the height at the top is 3 meters. So that means that we can assume that the height down at the bottom is 0. And then, as usual, when we're lifting an object, we can assume that the velocity both begins at 0 and ends at 0. Okay? And the other thing we know is that this entire process takes 4 seconds. That's how long it took for Roy to lift it. Okay? Now, in order to calculate power, we need to know how much work Roy did and divide it by the time it took him. Clearly, the time is 4 seconds, but we got to find the work that was done. So one of the things that we've learned earlier this chapter is that the work done by Roy, which is a non-conservative force, would just be how much the total energy changed. So I'm going to take TE final and subtract TE initial. Okay, so what I got to do is I got to figure out how much energy the box started with, how much energy the box ended with, and then subtract. So here we go. Since the height at the bottom is 0, that means that the GPE at the bottom is 0, right? Since the velocity at the bottom is 0, that means that the KE at the bottom is 0. And therefore, our total energy that our box has got before Roy lifted it is exactly 0 joules. All right? Then he lifts it. So when he gets it up to here to a height of 3 meters, now it's going to have some GPE, right? So we should, somewhere off to the side, calculate how much. So let's do it. GPE is mass times acceleration of gravity times height. So the mass of the box is 20 kilograms. Acceleration of gravity is 10 meters a second squared, and the height is 3 meters. Multiply it out, and you will get 600 joules. So after Roy lifts the box, it's got 600 joules of gravitational potential energy. Since it's ending at rest, we can assume he, sets it on a shelf or something. The KE is back down to 0. So the total energy that the box ends with is 600 joules. It changed because Roy did work. So let's figure out how much the total energy changed. So I'm going to go over here. TE final, well, let's see, it ended up with 600 joules of energy. It began with 0 joules of energy. And so the work that Roy did is 600 joules. So now what we want to do is find the power. So remember, power is just the work that Roy did divided by the time it took him. So he did 600 joules of work. That took him 4 seconds. Divide it out, and you get 150 joules per second. The rate at which work is done. Roy did 150 joules of work every second. All right. Another way of saying that is he gave the box 150 joules of energy every second. So for every second that he was lifting it, he did 150 joules of work. He gave it 150 joules of energy. Okay? So that's our power, 150 joules per second. Now, to add one extra teeny little hiccup into this, we don't use joules per second. We use watts. All right, so 1 watt, abbreviated with a capital letter W, is the same as 1 joule per second. Okay? So our power here is actually 150, not joules per second, but 150 watts. Okay? So be careful there. A lot of times people get the W for work and the W for watts confused. Notice if it comes after the number, it's watts. Whereas if it was work, it would say W equals. Okay? So power, P, is measured in watts. W, work, is measured in joules. All right? So there we go. There's the power. Roy gave the box 150 joules of energy every second. That's 150 watts worth of power. Okay? Now, you guys have all seen watts before. Watts show up on light bulbs. So let's do a light bulb example. Here we go. It's going to be awesome. How much energy does a 60-watt light bulb use if it's left on for 12 seconds? Let's start by writing down what we know. 60 watts. Well, that's a measure of power. So the power that our light bulb is using is 60 watts. It's going to be left on for 12 seconds. I'm going to figure out how much energy it uses, how much work is needed to power it, right? Remember, work and energy are both measured in joules, so we're looking for the work. Okay? So if power is work divided by time, multiply both sides of that equation by t, and you get work is power times time. So here's all we're going to do. Let me do it up here. We got a little more room. Work is power times time. So our power was 60 watts times 12 seconds. All right, so you can do the math on this, and you're going to get 720. But 720 watts. Okay? That was watts, not watts. All right, so let's figure it out. Well, remember, you guys, a watt is a joule per second. So this is really 60 joules per second that the light bulb is using for 12 seconds. The seconds cancel out, and you're going to be just left with joules. So 60 times 12 is 720, and you do, in fact, get joules. So that's how much energy our light bulb uses. 60-watt light bulb, if it's left on for 12 seconds, will use 720 joules worth of energy. All right? So the problems you're going to be solving are very similar to the ones we've been doing, where we've been doing work. The only difference is either I'll ask you to find the work, and then at the end I'll ask you to use that to find the power, or at the beginning I'll give you the power, and you'll use that to find the work. So, I guess that is it. So there you go, power in 7.5 seconds. Have a good one.